So our second talk today is by Ruth Britto from Trinity College, and she will tell us about from positive geometries to a coaction on hypergeometric functions.
Okay, thanks very much for the invitation and for the chance to present this work. So I'll mainly be talking about this first paper here, which appeared in collaboration with Samuel Lebreu, Claude Dure, Enan Gardi, and James Matthew. And at the end, I'll take the chance to show more of our process here in this longer talk. And towards the end, I'll just touch on an application in this more recent paper. So first, the motivation for constructing a coaction on hypergeometric functions comes from a few considerations. So first, there's a well-known coaction on multiple polylogarithms, based on which I, with most of the same co-authors, conjectured sort of physical coaction that's compatible with that on Feynman diagrams, which we've explored extensively at one loop and on a number of examples at two loops. And so this is consistent with the evaluation of the diagrams and with their expansion in multiple polylogs in dimensional regularization. So at this point, let's already note that this one is well established due to Goncharov and Brown. This one is conjectural, but it does fit in a framework of a very general coaction construction, which could apply to both of these objects by Brown. And now, leading into the subject of this talk, we have just the fact that Feynman, or observation, that Feynman integrals are generalized hypergeometric functions when evaluated in their closed form in dimensional regularization. So, taking all these concepts together, it would suggest that if we have a coaction which is compatible between the diagrams and their expansion, that at some level this should also hold for the Feynman integrals interpreted as in their closed form as hypergeometric functions. So that's what we've started to flesh out here. So all these are three coactions then, one on diagrams, one on multiple polylogs, one on hypergeometric functions, and they should all be mutually compatible. And the hope, which has in some cases been realized, certainly for the MPLs, is that there will be applications related to computing things, Feynman integrals more effectively, notably through the way that coaction plays nicely with discontinuities and differential operators. So this all fits with what's called a coaction principle. And the construction of the coaction that we outlined in this paper has since been proven by Brown and Dupont for the hypergeometric functions that are Loricella FD in their polylogarithmic case, meaning that the parameters are expanded around integer values. And let me make my usual disclaimer that formally, if we're talking about mathematical coactions, we should really be careful to distinguish the two entries in the coaction, and we should make a distinction between motivic and de Rham multiple polylogs and hypergeometric functions and so on, or properly use single valued versions, and I will basically be glossing over that distinction. So to show a first example, here's a very simple Feynman diagram, and it's related to this, well, to the basic hypergeometric function, Gauss's 2f1. Here, this is meant to show, normally the thin lines would be massless, so we have one massless propagator, one massive one, but of course the external line here is also off shell, so we have m squared and p squared, two scales and one dimensionless variable. This is evaluated, I should say, as a scalar integral in 2 minus 2 epsilon dimensions in dim-reg. So just to show very loosely, actually, what we mean by a diagrammatic coaction, so I'm not going to explain this here, but it involves taking our diagram and then applying a coaction. We find the coaction can be expressed in terms of other Feynman integrals, which must involve cuts. That's what these red lines indicate, that those propagators are on shell. And some diagrams are also obtained by contracting propagators of the original diagram. Now, in terms of so this is, of course, the same diagram of the previous slide. So this is a 2f1 function here. The cut, this maximal cut here, is a leading singularity. So this is just power functions. And then what this is our tadpole, so also something simpler. And what we have here is what will also be a 2f1 function, a different 2f1. So if this is compatible with a coaction on hypergeometric functions, this is showing that the coaction of a 2f1 will match what we've got here on the right-hand side. So it will be expressible in terms of 2f1, possibly simpler functions, which can also be recast as 2f1s, just with some degeneracies. And then just to remind you that the claim is that both of these will be compatible with the expansion in epsilon, which gives logarithms and polylogarithms, and that will hold order by order in epsilon. Now, the foundation for the coaction we're going to lay out on hypergeometric functions is based on the Euler integral representation of the hypergeometric functions. So for 2f1, now let me write it out. So 2f1, the hypergeometric function would normally be defined as a hypergeometric series first, and then you would notice that it also has an integral form, but we'll just start with this and can really take it as a definition if we'd like. So we've got some gamma factors out front, and then it's a one-dimensional integral, and we have 3 factors, u to the alpha minus 1, 1 minus u, gamma minus alpha minus 1, 1 minus u x to the minus beta. And we're, whenever we encounter one of these hypergeometric functions, we're going to look at the integral part. I'll come back to the gamma functions in a moment. And we'll just write this in the form integral over the contour gamma, which here is integrating from 0 to 1 of some differential form, which is the integrand. So here I'm disregarding the gamma function factors. Let me just say how we can deal with them. So going forward, the gamma functions, the point is they behave very nicely under the coaction. So this can be taken as almost the first case. It's not exactly hypergeometric, but it fits with the notion of resumming the whole series. So if you take this, say gamma of just 1 plus epsilon, that's a simpler one, and just to make everything come out nicely, we include the prefactor of the Euler gamma, which we'll also conventionally include in Feynman integrals. So this is exponential of a series, which can be expressed very simply in terms of zetas. And so it follows that the coaction, if you just take it order by order with a known coaction on zeta and then resum, that this object is what we would call group-like, meaning its coaction is just the same thing, tensor itself. And from there, it follows that if inside the gamma function we have some other integer, plus some complex number times epsilon, that the factors, I mean, using the basic property of the gamma function, that x times gamma x is gamma 1 plus x, we can extract factors here until we're left with the integer 1. And those are all rational, so those just pass through the coaction, and those can just go back then into the first entry. So what we would find putting them back is that we have sort of the same original gamma here, and then in the second entry, we would have just 1 plus a epsilon. So I'm going to use this property to just ignore the gammas for the main part of the talk. We're going to focus on this part, but this is what we would do to replace the gammas properly at the end to write down a really explicit coaction formula. Maybe I should pause if there are any questions at this point about gammas. No?
So does it work for every A now? I mean, how should I? Yeah.
Oh, okay. So I'm expanding in epsilon. So just imagine that I'm expanding. I mean, I expand in a epsilon. So a, yes, will also just be treated as some rational number or something that's not.
Okay.
There's no non-trivial coaction on a. I mean, okay. So in the context of Feynman integrals, you'll see. Let's see, what should it explicit? I mean, basically we'll have things kind of like this, right? It'll just be, there's one epsilon, but then it will come with, I think in Feynman integrals, maybe even always integers if you're in dim-reg. But when we do the mathematical treatment, we'll just say that it's a complex number, constant. Thanks. Anything else? Okay, so now we're looking for coaction of this kind of integral. And so this leads us to a very, what we call the master formula, which is a very general kind of coaction on integrals. So that is that a coaction on integrals of this form will be expressed as a sum of these kinds of terms, where in the first entry of the coaction, you've changed the integrand. And in the second entry, you've changed the integration contour. And this gamma and this omega are the same as on the left-hand side, what you started with. And here you just have some rational coefficients to be determined. So all the three coactions that we proposed have this kind of structure. And the statement of this formula is that there exist sets of integrands, integration contours, and rational coefficients that make this true. This kind of formula satisfies the axioms of the coaction. You can see just by acting twice, it's co-associative. You'll just expand this further. It's really like inserting a complete set of states in physics terminology, where now the integrands we're inserting are just some generators of the cohomology associated to the integral. And likewise, the integration contours gamma j generate the homology. So in the case of the hypergeometric functions in the Euler integral representations, we'll have an integrand that's of this form. So we have some number of variables, integration variables n. So my underlined u, which is boldface in the paper, represents the sort of multi-index variable. So differential form, and then the rest of the integrand is a product of polynomials in those u variables raised to some complex powers. Then, correspondingly, the contour is not unrelated to the structure there. We're sort of integrating between branch points, so this gamma can be taken as an n-dimensional cycle in the complex projective space where we've cut out singular space specified by the zeros of the polynomials. So in the case of the 2f1, we showed we have that these would be the polynomials, u1 minus u1 minus ux. So there are 3 zeros, and indeed we're integrating between some pair of them.
Is your contour always a real contour, or then you, at some point you will go to closed contours on the complex plane?
Yeah, no, that's not, everything is essentially complex.
But they're open contours, they're not closed contours really, right? They just go between branch gaps.
That's right.
That's
so
right.
So you're integrating from 0 to 1. I guess if you're going to be careful, you should set up the twisted cycles. So I'll come to the twist shortly. So yes, so indeed what we have here is, let me then outline how we're going to actually set up the coaction to identify what these ingredients need to be to make this work for the hypergeometric functions we're interested in. So here, where we're looking for generators of homology, so cohomology, so it's a basis of what will really be twisted cohomology. And the twist is coming from the fact that we have these exponents of the polynomial, so they're not single valued. And these gammas are going to form a basis of twisted homology. So what do? We can choose these bases independently, and then in a nutshell, given the 2 bases, you can then derive these coefficients from intersection numbers. And having positive geometries where available is going to help give us some natural choices and really make the computation easier. And that turns out to work for all the examples we studied in detail, that we could identify the basis of twisted homology in terms of positive geometries.
Can you find a diagonal basis in which the C will be a diagonal?
And I will show you that too. Okay, so the first step is, as we're looking for a basis, is to compute the dimension, so we know how many generators we're looking for. And the dimension of homology and cohomology should be the same, which is the size of the basis. And formally, you get this from Morse theory or a computation of an Euler characteristic. In many cases, which include all of ours, a simple way to get it is by looking at the critical points of a twist, which are the solutions to d log phi is 0. So I haven't yet defined phi. So we'll come back to this in the context of an example more explicitly. Then the next step is to choose the basis of your contours. So a good way to do this is to identify some positive geometries. And this is really laid out in the paper by Arkani Hamed, Bai, and Lam, which means we're looking for differential forms with unit residues at their boundaries and with the associated recursive structure, although we don't really make full use of that. And we identify them within this space of singularities. And what's important to us is that we can use the fact of being positive geometries to construct these canonical forms, which we're going to need to derive the intersection numbers. So some cases in which we know that these positive geometries are guaranteed to exist are where all the polynomials are linear. We see that several times. Or where they're mostly linear, maybe there's one quadratic. And in those cases, we can construct canonical forms, and we've made good use of that. Okay, next, we'll choose the complementary basis of differential forms. And if you like, since we have canonical forms, if you've already found a basis of gammas, then you can simply take these canonical forms to be a basis as well. So that's fine, or any other basis. And actually, if, as Tomek was hinting at, if we're going to want to get a diagonal matrix, then really we don't want to take exactly the same basis, but we'll see that in examples. Great, so then we have the gammas, the omegas, and now from those we can compute the cohomology intersection numbers. Which we'll write using bracket notation. And we use various helpful formulas of Misera to do this. Once we've done this, then we can invert this matrix of intersection numbers, and the entries of the inverse matrix are precisely the coefficients we need. So the reason we needed the canonical forms is because, I mean, what we really have is, basis of homology and cohomology, and really the only natural pairing between those objects is, well, the form of an integral. If you have a differential form and a cycle, then you can integrate the cocycle over the cycle. But now we want intersection numbers, which means we have to map these to cohomologies so we can do this different pairing. There are also homology intersection numbers, and it could be interesting to look at those as well, but actually it's the cohomology intersection numbers that are very clean, that are really just rational numbers, at least in the cases we're looking at. So that's what we get from the existence of canonical forms.
Can I confirm that I understand the point 2 correctly? So when you talk about positive geometries, we always have some complex space and some real part of this space. So these contours here, they are the real parts.
They're on the real part, that's right.
Okay.
But could we continue the real part or deform the real parts to the complex part? Because you mentioned that we are working in projective.
That's right. And if you're going to really use twisted cycles rigorously, then you would need to do that.
Yeah, like for example, the 0, 1 for the 2F1 cycle, we can like circling around the 0, circling around the 1,
yes.
Right? In the complex plane, right?
Yeah.
Yeah. So sorry. So what is the logic then? So you use positive geometries to find the real geometry, and then you take this real geometry and make it into a twisted cycle. Is that correct?
Yes.
Okay.
And okay, let me also say, I mean, I'm emphasizing the links to positive geometry because of the nature of this workshop here, but it could be that maybe there certainly are other ways to think about it. And it could be that maybe it's not the best, but it's certainly interesting to probe whether there is a very deep connection here or not. But okay, that's not guaranteed. So for example, in the proof of part of the analogous statement done by Brown and Dupont, they used what Brown called a C0 map. Right? So they didn't really depend on positive geometries. But I think it's essentially the same thing. A C0 map, it gives you a canonical form where it exists. And maybe it wouldn't always, but for them, for the Larachello function, certainly it did. So this is something that deserves further exploration. Okay, so to make this concrete, let's go to the case of 2F1 and see in detail what's happening. So here, again, this is the integral part without the gamma functions, which we've set aside. So this, first of all, we'll just rewrite it in a really trivial way, but just to make it match the notation we're using. So I'll just rewrite all the exponents to show explicitly that we're going to have them expanded around integers. So it's not some arbitrary 2F1. And So for each one, I'm giving independent labels to the exponent, where the n's are the integer parts and the a's are just complex numbers. Okay, now we'll look at our integrand carefully, this differential form. And we write it in this way, capital phi times small phi, where we're separating the twist from the other part. So the phi in our notation will be the single value differential form. So this is just taking the differential along with the integer parts. And then capital phi is the rest, which is a multi-valued function. Yeah. And this, okay, we'll call d log phi is what's called the twist one form. So this is the twist that's giving its name to twisted homology and twisted cohomology. And as we are looking at sort of for the coaction, and we're going to be, changing the contours, we're going to be changing the integrands, but this twist is going to stay constant throughout. So as we choose our basis, say, of differential forms, we will look for differential forms like this, but then we'll choose some specific values for the exponents. But here we're going to just stick with basically these variables, a0, a1, ax. So one way to count the dimension of the basis in this example is to check the number of critical points, which is the number of solutions to d log phi equals 0. And that has two solutions, because if you look at it, you got a quadratic polynomial and the one variable u. And so we're looking for two generators of homology to begin with. So we can draw a picture. So this is indeed the real part of u. And we pick out the singular points. So our phi has both phi's. The capital phi in particular has its singularities at 0, 1, and 1 over x. And it is this, okay, and now we can use the terminology of hyperplane arrangements to see, if we want to integrate between branch points, well, actually it's not hard to see, you can get only two independent ones, which fits with what we know that 2f1 is a solution of a two-dimensional differential equation. So we have two independent solutions. Now we can interpret this as an arrangement of hyperplanes, which we get whenever we solve for the zeros of these polynomials. So the fact that all these polynomials are linear means that the solution of each one separately is a hyperplane, and when you put them all together, you get an arrangement. Arrangement means we're paying attention to where they intersect. Now here, these are all just separate points, so they're not intersecting. Nevertheless, they sort of split our region into different parts. And one way to read off a basis is to take what are called the bounded chambers. So bounded chambers are easy to see visually. They just are the finite parts that are bounded by the singularities. So there are two of them. Otherwise, we go off to infinity. So there are two bounded chambers in this hyperplane arrangement. it's going to look more like something when we get to our two-dimensional examples. So we can choose these two bounded chambers to be our basis. Instead, here, actually, I will come back to that choice later. But first, let's choose a linear combination of the bounded chambers rather than the ones themselves. So let's take for the first one, the integration contour from 0 to 1. And for the second one, instead of integrating from 1 to 1 over x, I'll combine it with the other one. So we start from 0 again. Right, I can choose to do that. And so given these bounded chambers, you can easily construct the canonical forms. And it's easy to construct these D-log forms for 1- and 2-dimensional arrangements. So they take these simple forms, and you can see these have the properties we want, unit residues at their boundaries. And there are D-log forms. Is this clear? Let me pause for questions.
Sorry, you mentioned that the hypergeometric function 12(1), they have two cohomology and homology bases, and the solution of the hypergeometric function is also 2. And would this conclusion be generalized to these hypergeometric functions like 3f2 or other RPL functions? Like we have RPL F4 with the cohomology are the number of cohomology bases are 4, and then the solution of RPL F4 differential equation are also contain.
Exactly. Yes, that's right.
So they are like 1-to-1 match, the number of solution and number of independent bases.
Yes.
Yeah. Okay. Thank you.
Yeah, I mean, in a way, that's the way to fill out the cohomology. I was saying the differential operators are just acting on the integrand, and we construct it so that, I mean, the surface terms are not going to contribute because we're always integrating between the branch points, or from the zeros of the polynomials. So if you fill up the basis, then you should get all the solutions to the pertinent differential equations. Okay, so now the first option, if we want to take differential forms, our basis of differential forms, the omegas, is to take precisely these ones, well, for the phi's, actually without the twist, and then reinsert the twist. And then doing that, so now is the time to introduce the formulas for cohomology intersection numbers that we're going to use. So for n equals 1, one variable, which is the case we have in front of us at the moment, you can just read off the residues. And this is, so when you take the cohomology intersection numbers, it's always with reference to this fixed twist that's staying there for the whole problem. So you read off the residues, and actually this formula is very, very simple, because if you're using the canonical forms, you're getting unit residues at their boundaries. And so you just pick up the residue from the twist, which is essentially reading off the exponent. Very simple. This kind of formula has also been generalized to larger n by the Frelsvig, Gasparetto, Mandel, Mastrolia, Materazzi, and Misero. And the other formulas we found useful are if you don't necessarily have a D-log form, although actually we do, but you can use this other formula in terms of a Hessian matrix, where, okay, so you take the Hessian matrix of the twist, and here what's meant by the hats, just to be clear, is the differential form with the differentials stripped off. So you just evaluate this at all the critical points. Say the U star is U such that D log phi of U star is 0, the critical points. And you can write this expression for the two-dimensional integrals as well. So to come back to our example, 2f1, now we'll use this formula. Let's take the basis of canonical forms. So if we've taken, okay, let me write. Just, I'm not sure if this notation is helpful or not. We can just rewrite the canonical forms without the capital omega for the sake of a cleaner presentation of the intersection matrix. And we take, right, these phi's, and then again, we would want to, the actual integrand corresponding to these in the coaction would be these phi I times the capital phi from the twist. Okay, so then it's easy to read off the intersection matrix of intersection numbers. So using that formula of the residues, and as I said, we're really just reading off overlapping singularities. And this is really the same form taken twice, just with different notation. So, right, so this has two overlapping singularities with itself at the points 0 and 1. So we're getting one contribution from the 0 and one from 1. With each other, they only have the common singularity of 0. So that's phi 1, psi 2, only this term. Of course, same thing for the other off-diagonal entry. And finally, from sort of the overlapping singularities there, we get another two terms. Now one is related to the point 1 over x. Okay, so we can invert this matrix to get the coefficients in this coaction formula. Just write it down slightly more explicitly, although I'm not going to actually invert the matrix here. So recall in the left entry, we're still integrating from 0 to 1 as in the original integral. And then in the right entry, we've got the original integrand here. And then and in one case, for j equals 1, we're still integrating from 0 to 1. In the other case, we're integrating from 0 to 1 over x. And you can, it's easy to rewrite that as a 2f1 just by a change of variables. Now, I'm not going to write this more explicitly because I want to then show the variation by which we can fall upon a diagonal matrix directly, if we like. So variation on this is just choosing a different basis of our differential forms, where the phi 1 and phi 2 don't need to be the canonical forms that we constructed. So we can get a simpler matrix by choosing phi 1 and phi 2, small phi 1 and small phi 2, to minimize the overlap of the poles. So these, let me change to green. So these contours are the same as before. Now we've changed these forms. So see, so this one has a pole at u equals 1, so that'll overlap with this one, but not with this one. Likewise here, this one picks out only the singularity at 1 over x, so it will give a 0 off diagonal entry with when paired with gamma 1 in the cohomology intersection numbers. So just to write this out again, here we get 1 over a1 epsilon 0 So now this is very easy to invert, and the coaction formula we get is, now I mean, it's the same as before, I'm just rewriting the omega as the phi phi, and we have these coefficients, phi 1, so this is the I mean, this is a form that we prefer. If we can get it to be diagonal, then we will do so. I wouldn't say we have a very systematic way to do that. You can do it just sort of by eyeballing it, by trying to minimize overlaps and see how well you do. So this, again, each entry here is manifestly some kind of 2f1. So here in these second entries, you're getting the same exponents in the integrand that you started with, and you're integrating either from 0 to 1. So this is exactly the same 2f1 as here. And this one is, as I was mentioning before, you can just change variables, integration variable to read that as a 2f1. And these first entries, of course, are also 2f1. And here you just have very special choice of exponents here. So phi1, and this is giving you just precisely a -1 exponent, say for this, times the multi-valued function. And likewise, here you get precisely a -1 exponent for this factor and 0 for the others. And it's also possible, and what's relevant for the Feynman diagrams is you'll want to take some degenerate limits of these cases. So for mathematics, it's for proving things in mathematics, often you'll want to say that these exponents are generic. There are no relations, especially among the a's, and they do not sum up to 0. Now that typically actually does not happen for Feynman integrals, but so we've checked how this works out in some small examples, and we find it's not a problem. We can take the limit, although it would be hard to do so if you wanted to construct a really airtight mathematical proof. Let me just close this example then by giving this in very explicit form. So now I've actually rewritten it in terms of the 2f1s and even replaced the gamma function prefactors and everything. There's some rational prefactor here as well. Here you can see, because we've changed a variable in this last term, that the argument has become 1 over x instead of x. And this is in one version of the coaction on 2f1 that is consistent with its epsilon expansion in multiple polylogs. And so we do also observe this general property here that from this has in the right entries, the coaction has produced for us, sort of spit out the second independent solution of the differential equation. So any questions here before I go on to other examples?
I mean, these logarithmic forms you found in the previous page, there are still canonical forms, right? But they're on different segments. They're on semi-infinite segments.
Sure, yeah, they're canonical forms of different geometries. Yeah.
Yeah. Okay.
So it's true, maybe it's helpful to still think about it that way. Now, certainly we like to have D-log forms because it does make the intersection numbers come out very nicely. Any other questions? Okay, so I'll show a two-dimensional example, which is at least more fun to look at than points on a line. I think now at least we have something that looks more like a nice hyperplane arrangement. So here, this is Appel F3 two-dimensional integral. We've got 5 polynomials whose zeros are depicted for their real parts in this figure. Right, so we have pairs of lines that don't intersect except at infinity, and one diagonal line. So here we can observe that if we're looking for the basis, okay, so it's good to note also that this hyperplane arrangement is not degenerate, meaning that there are no points where we have more than 2 lines intersecting. And in that case, we can read off the dimension of homology, or even a basis of homology, as the bounded chambers, as mentioned, and now we can really see them a bit more nicely. So here's a bounded chamber, here's one, and here's one. That's 4. Everything else goes off to infinity. Mhm.
What would happen if you pick x and y in such a way that they intersect in one point, 3 of them in one point? You could do that, right?
Oh, for special values of x.
Yes.
That's true. That could happen.
It does mean that the basis reduces to one lower, or one cannot use discounting at all?
We can, okay, I'm not sure, I wouldn't say we've checked every possible limit. We certainly have checked in several cases that if you just take the coaction formula in the generic case and then go to a limiting value, that you just get a consistent coaction formula. But yeah, I guess if you wanted to start here with, yeah, if you landed on a non-degenerate, sorry, a degenerate arrangement, then yes, then you could also consistently derive the coaction, and you'd have to blow up the degenerate point, point of degeneracy. And we also have done that in some cases.
But isn't it true that the dimensionality of the cohomology does go down, right? I mean, if you lose, like if you shrink one of those triangles, it's always a number of bounded chambers, and it just goes down. Isn't that correct?
So it's always the number of bounded chambers, even in a degenerate arrangement. I'm not sure of that.
Even in the degenerate case. And I think in fact this way of thinking in terms of the canonical forms of the bounded regions makes it natural, because so long as, for example, you take the one of the little triangles in your example bounded by D, G, and C. So long as they're not literally going through each other, it's true that as you make that DGC triangle somehow smaller and smaller by lowering the horizontal line, it looks visually like the region is getting smaller and smaller, but the canonical form is always sitting there, and there's always has a residue, and the residue is always 1, except for literally the case where DGC pass through each other, the numerator of the canonical form becomes exactly 0. You lose the form, and you also reduce the size of the basis at the same time. So I think this fact about hyperplane arrangements is completely general, that the dimension of the twisted cohomology is always given by the number of bounded regions, even in the degenerate cases.
Okay. Okay, good. Yeah, certainly I don't know of a counterexample, so that's fine. Okay, so here, sorry, okay. We can choose a basis, we can choose the bounded chambers, but here what we chose the bounded chambers that I just showed, but for the sake of reconstructing the integrals at the end, we chose, again, linear combinations of them such that these all form triangles. And the nice thing about that here, I should say this is optional, right? So you can choose any basis you want. You can take literally the bounded chambers and their canonical forms, and that's fine. And you can just derive, as long as you can find your way to computing the intersection numbers, then you can derive the coaction. Okay, but to make it look nice, say we chose these ones, which are, so for example, ABG here, this is actually the original defining region. So this is some combination of three bounded chambers, which corresponds precisely to what's given in the definition of LF3, or the Euler integral representation. Okay, also just to present the results, let me also write the twist, or not the exponential of the twist. So this multi-valued function, I'm just going to label the exponents with the same letter labels that I've put on the lines. I'm showing what the exponents are because they're going to come up in the intersection matrix. So, okay, again, we know very well how to write canonical forms for triangles, right? It's just d logs, and you put ratios of the linear polynomials. And so for the basis of integrands, we're also going to choose them to minimize overlaps. So we'll choose phi AB, and that's going to be one that has poles on the A and B lines. So explicitly, this is d log U wedge d log V. Let me not write out all the others in d log forms, but they're all very similar. We also take phi BC, phi CD, and phi DA. Now, by the way, if you wanted to convince yourselves that these were linearly independent, an easy way to do that is also just check their cohomology intersection matrix with themselves and check it has full rank. But okay, to construct the coefficients in the coaction, we're going to take the intersection numbers of these phi's with the canonical forms of the gammas. And there, we can also just immediately get that it's diagonal. So we have I had it the other way around before. So, okay, in the appropriate order, we have a pair. And you can just read it off, actually, right? So they all correspond to two overlapping boundaries. We want two because it's a two-dimensional integral, and then there's this line G that I haven't used in constructing anything here. So it's just the diagonal matrix, 1 over AB epsilon squared, 1 over BC epsilon squared, 1 over CD epsilon squared, 1 over DA epsilon squared. Trivial to invert, and you get a coaction formula very much like before. And yes, you can use the fact that these are triangles in this case to rewrite everything nicely as F3s if you wish. And this construction generalizes to the full family of Loricella FB. So you can larger numbers of, n-dimensional integrals. Okay, so now come to a much harder example, which is Appel F4. And
sorry,
here I've written
down. Example, can I ask a quick question about the previous case?
Yes.
What do you know what would have happened if we? I mean, if you're probably it won't make the matrix diagonal or anything, but I wonder if anything nice happens if you directly choose both the regions and the basis to be given by the bounded regions and their corresponding canonical forms.
Well, I mean, then you get sort of all possible overlaps, right? You get a
you get
effectively non-diagonal matrix. Well, we have done that. We have
the overlaps reflect the sort of geometry in some interesting way. Like you know, we have all these regions and they touch in certain patterns, right? Like some of the, you know, you have these triangles and pentagons. All the triangles touch the pentagons, but two of the triangles don't touch each other, and so on. I'm just curious whether you guys have looked at, in this example or other examples, whether the sort of geometry of the hyperplane arrangement and how the regions overlap and the codimensions on which they might overlap in higher dimension examples, is that reflected in some simple way in the matrix or not?
Okay, well, I mean, it is, I mean, just like this, yeah, you could, I guess, if you were taking, say, this pentagon, right, with it's canonical form with itself. Yeah, I mean, that's true. I mean, you could just write down the intersection number based on these lines.
Yeah.
That's all. Okay, but
yeah, I'm just wondering. But
I don't see any reason to prefer that form of the coaction. So we don't like integrating over pentagons. If we're going to be checking, the MPL expansion, for example.
Sure. Right. Yeah. Right. Yeah. I mean, I understand why you're doing what you're doing. I'm just curious for other purposes whether this whether the structure of the matrix that shows up there reflects the geometry in some simple way or not. But okay.
Well, yes. I mean, it is showing you where the intersections are. So. Yes, it contains all that information. But
all right. Yeah.
Okay, yeah, I don't think it's okay from the point of view of the matrix. Yes, you can read off the intersections, but I don't think there's any sense in which taking the bounded chambers would improve anything
Okay,
or make it more visible than anything else.
all right.
I mean, especially because, I mean, you can move these lines around, right? You can
Mhm.
move this line so the intersections
Sure.
are here, and then the bounded chambers would look different, but the intersection matrix would be the same.
Of course, if you did that, you'd also change, I mean, by this philosophy, you change what the canonical, I mean, you would always choose the bounded chambers and the canonical forms of the bounded chambers. So I agree, as you moved it around, it's not convenient for that purpose, because that would also change, but okay, all right.
Yeah,
it was
and
a
really
very
the
good
intersection
question.
matrix, I guess, doesn't care about that information at all.
Yeah, okay, all right, thanks.
Sure. Okay, so here, this is what we started with, and this looks like another two-dimensional Euler integral representation. This one gives you a hyperplane arrangement that, so you'd have 3 parallel lines for U and 3 parallel lines for V, and then you have a kind of diagonal line. Okay, yeah, this is not the greatest drawing, but I want to show it's not going through that other point. But there are degeneracies here. There are degeneracies at this point and at this point. So you can try to go through the analysis, but it would require blowups. Oh, and actually, yeah, okay, so there are very interesting issues here, because this is problematic because, we've got 7 factors. I've drawn 7 hyperplanes, but we don't have 7 independent exponents. In fact, right, we only have 4 parameters. And so that causes problems. So, I mean, if you would look at this, you might read off 7 bounded chambers, and that's fine, but that doesn't correspond to the true dimensionality of the holonomic system for IPhT. In fact, the dimension should only be 4. And if you set up the twist polynomial and count the number of critical points, taking into account that these exponents are all related, then you do actually get 4. So this is a case where you'd have to watch out and not take the picture to be the end of the story because of those relations. So, I mean, the fact that these exponents are related maybe also really means that they're not exactly polynomials being raised to the exponents, right? So, for example, if we look for alpha appears here and here and here and here. So really it's some rational function like this being raised to the power alpha and not a linear polynomial. Okay, so it's possible to proceed with this picture, and we did spend a lot of time on it, but it's very delicate for these reasons. It's better to use a representation called the Kummer representation of IPhT, which is this. So this is another kind of integral representation, but now we have a quadratic factor. And now the integration region here is also something in twisted homology, where I've just copied this figure from a paper by Goto Matsumoto. So, okay, so here what we have is T1 and T2 are variables. L is the linear factor, and this is the quadratic one. So now we're sort of integrating in this region bounded by L and Q, but also something weird is happening in the twist. So I never really talked about the twist in the previous examples because the twist was there, but it was always just a tiny little tube around the boundary. And now we have this strange thing where the tube or the twist is going around 2 of the boundaries simultaneously. So it's a bit more sophisticated construction. But okay, you can proceed with this, and this is nice. It's a bit more direct. So the benefits of using, and in this paper, there were given not only this integration cycle, but in fact the full basis. You can choose a basis of 4 independent ones. each one giving an explicit F4, appel F4 form when integrated. So that's nice, but they're not easy to draw. In fact, one is an involution, so you can't even draw it at all. So, okay, we took the basis of cycles from this paper. Then we chose a basis of suitable D-log forms to go along with it there. And based on that, we constructed a coaction for appel F4, which we checked. So I think I am.
Are this the logarithmic forms, canonical forms for some of these regions there? Or, I mean, if I take phi1, is it a canonical form for any region depicted in the picture?
That one, I guess that one is. Yes. Sure, because that's just bounded by T1, T2, and L, right? So that's really just like a triangle.
What about the other ones, the more complicated ones?
The other ones, oh, well, no, yeah, these are fine. So this one's fine too, right? It's just D-log. So that's really like T2 and L, I guess, right? And this one's fine too. So this one is D-log for, okay, but now we have something. Now, yeah, now this is involving X and Y, which are not really so visible in the picture. Yeah, you don't really see a T1 minus X. Okay, so this one is a bit of an oddball. The other ones are easy. So yeah, there also were a basis of twisted cohomology given in this paper, and here we just adapted it somewhat to, I guess, so to make perhaps I don't remember the distinctions exactly. I think we did make these ones nicer to fit the picture, as you say, and to give nicer intersection numbers. This one we might have taken directly from the paper.
Sorry, Ruth, I think you explained it and I just missed it. Where did these curvy things come from? You started with you started with all these lines. Where did these curvy things come from? Where do these quadratic things come from?
Just factoring me?
Yeah.
Oh, this is very different. No, I don't. I certainly offhand I don't know a direct change of variables from the other representation to this one. And yeah, that's not the way to approach. So it's not that you look at this and then you think, well, that's not suitable, so we'll repackage it. No, to get the Kummer representation, there is an algorithm which was laid out by Kummer. So if you follow the algorithm, then you will land on such a representation.
I see, but this
I don't remember the details, but no, you don't start from there. It's hard to find good representations. I guess Kummer's algorithm is helpful in this case, at least.
I see, but the sort of magic is that in the previous way of writing things, you had rational functions raised to powers, and now there's some way of rewriting it in terms of just polynomials raised to powers.
Right.
Is that right?
Yeah, but I wouldn't say rewriting. I think to get the algorithm, this would actually start from the series. You start from the series representation. Okay. Then Kummer has an algorithm to turn that into an integral.
Rewriting, but there's
and it doesn't pass through the other
remarkable equivalence between these two things. They're right. I see.
Yeah. So right, I've never passed directly between these two representations.
Interesting.
And I guess there could be other ones out there useful for different things. Yeah, there are a lot of mysteries in hypergeometric functions. Okay, I am pretty much running out of time, so I did want to touch on these configuration space integrals over punctured Riemann spheres. And by the way, I was planning to write out, but I can leave that till questions later if we want to wrap it up now.
Maybe let's do the following. Let's thank Ruth for the talk.
Okay, no, well, let me just flash my summary slide at least.
Sorry.
Okay, so there, we proposed in summary, we proposed a coaction on generalized hypergeometric functions based on their Euler integral representations, and it takes this form, the master formula, and so we've done this in the case where we have product of polynomials in the integrand, and we're integrating some boundary among the zeros of those polynomials. and it's compatible with the coaction of multiple polylogs with when the exponents are expanded around integers. Okay, thanks.
Okay, so now let's thank Ruth for the talk. Yes, and then we can proceed with some questions. And if there are no questions, then there's a few minutes you could come back to the to the last slide which you wanted to explain. But if there are a lot of questions, then we probably move.
Sure.
Okay, so are there questions? Okay, maybe so let me ask the question. What was the slide you wanted to explain?
Okay, sure. I'll try to go through this fairly quickly. So yeah, so another recent application of this idea was to these configuration space integrals for punctured Riemann spheres. So okay, let me just say that we've got n is the number of punctures on the Riemann sphere. P is the number of integrated variables. So these are very closely related to tree-level open string amplitudes in the case P equals n-3, right? So we've always been moving 3 of our points to 0, 1, infinity, and then you can integrate over the remaining variables or not. So we're exploring the case where you might want to only integrate over a subspace of the remaining integrals. So this is configuration space labeled by n and p. So the case p equals n-4 also arises in string calculations, and this general configuration space also shows up in correlation functions and CFTs and the Coulomb gas formalism. So okay, so let's consider for fixed n and p what the integrals we're looking at then would be integrals with some Kobe-Nielsen factor. There's really this same kind of structure. So the Kobe-Nielsen factor is now in the role of this capital phi. This has all the pairs zi minus zj raised to the powers of the dimensionless Mandelstems. So now this is included alpha prime. And if we're going to match to expansions of multiple polylogs, we're now expanding in alpha prime rather than epsilon. And so here the dimension is n-3 factorial over n-3 minus p factorial, and as I've pre-drawn here, this is the kind of hyperplane arrangement we're looking at in the case of p equals 2, where I can draw in 2 dimensions. So let's say in this case, these are the 2 integration variables. Say these ones are the fixed variables, and you get a generalization of a Selberg arrangement. So here we do have points of degeneracy, so we have to tread carefully. But indeed, the number of dimensions does match the number of bounded chambers, and we can proceed, and we take the cycles to be the bounded chambers. And from, I'd say that case p equals 1 precisely reproduces the Lorentz function. So there again, it's just points on a line. That's exactly like what I was showing for 2f1. And you can take the bounded chambers, and then we construct the basis of differential forms. So to be just from these ratios of S over Z. So for example, we might take omega 1 to have some poles in Z2, and then some poles in Z3. And so on. And this corresponds to setting up forms such that when you look at the bounded chambers, these also lead you to a nice diagonal identity matrix basis, because they're constructed precisely so that the residues will cancel between the endpoints, between the boundaries of the bounded chambers. except of course for the diagonal entries. And so we've given explicit formulas for general N and P. And I just want to mention that the case pertaining to the string amplitudes P equals n-3 does reproduce the coaction proposed earlier by Schlotterer and Stieberger, where everything is integrated, so it's a coaction in terms of multiple zeta values. Okay, let's leave it at that for now.
Thank you. Thanks. Do we have some more questions for Ruth? No.
Sorry, you. Go ahead. Yeah.
No, go ahead.
Yeah, Ruth, you mentioned that because during your talk, the time is limited, so I didn't ask further. You mentioned that the differential equation for the definition of the hypergeometric function could determine the dimension of the cohomology and homology group. And you mentioned that it's acting on the integrand and some boundary turn stuff. I didn't actually catch that. Could you say this again or more in details?
Yeah, so we're looking for the full basis of cohomology. So that means we're putting in all possible integrands, but then they're that can be obtained or that are equivalent up to integration by parts relations, along with whatever trivial manipulations. So
integrands? Which the one like a twist and the basis stuff.
So yeah, I mean, as long as this is the integrand really just is a polynomial times the differential, where the everything is, or at the boundaries of the integration contour, you're getting those are set to 0, then you can really just act with the differential operators on the integrand without introducing any additional mess from the integral. So
yeah,
differential
operator are the definition or the definition of the hypergeometric function, the differential operator, right? Or right?
Mm-hmm.
But what do you mean differential operator? The definition of the hypergeometric function.
Well, I mean, you can just start differentiating and then you'll derive the differential equation satisfied by the integral.
I think
right, because you have the polynomial, so you're just playing with the exponents, and eventually you'll have some system of equations.
Oh,
which leads you to the differential equation.
Ruth, I think
or a system of differential equations. Yes, Nima?
I think the question is whether it's tautological, because the hypergeometric equation satisfies the differential equation to begin with, but it's not the same differential equation Ruth is talking about. The hypergeometric differential equation is second order. Ruth is talking about this first order system for all the integrals that you could talk about, and you could get the hypergeometric one from the more fundamental first order one just by applying it a number of times.
Yes, thank you.
So it's not true that the hypergeometric already gives you this. What Ruth was talking about is the more fundamental starting point from which you can derive that second order equation. And in these larger systems, there would be higher order equations that you would get in that way.
Oh, I see. Thank you. That's very clear.
Okay, Einan, I see that you are coming in.
Yeah, I just wanted to say that the answer to your question, there is a good example in Appendix B of the recent paper that precisely shows how you get this second order differential equation for the Appelle 4 case from the first order equations. So yeah, so the answer is just in Appendix B of that recent paper that Ruth mentioned.
Oh.
Yeah, thanks, Einan. I wanted to say it would probably be helpful to look at a nice two-dimensional example to see how these things work.
Is it the 2106 or the 1910?
The one from this month.
Okay, the 6th in June.